This is a tutorial for homework number 12 on rotational motion. And in the first problem, we have to convert 60 degrees into x pi radians and into some value of radians without the pi. So to solve this problem, we first have to convert, remember the conversion of degrees to radians. So we know that 180 degrees is equal to pi radians. So a factor of 1 will be equal to pi radians divided by 180 degrees. So to convert 60 degrees into radians, we just multiply 60 degrees by 1. And that would be the same as multiplying it by this conversion factor where we have degrees in the bottom. So this degree will cancel out. And pi radians in the top. And that comes up to be 0.33 times pi radians. So that gives us x, and then to convert this into radians without a pi, we just have to multiply 0.33 by 3.142, and that comes up to be 1.05 radians. So we're given a couple of other angles, and we have to convert all of them using this method. Right, so for problem number 2, we told that we have a grinding wheel. So a grinding wheel here is a cylinder, and it has a diameter of 0.25 meters. So the diameter tells us that the distance here is 0.25. So if the diameter is equal to 0.25 meters, the radius is going to be diameter divided by 2. And we told that it's rotating with a frequency of 2,000 revolutions per minute. And we're asked to calculate its angular frequency. Alright, so before we do that, we first have to convert 2,000 rev per minute into revolutions per second. So that will mean multiplying this here by 1 minute over 60 seconds. And to get the angular frequency, we have to multiply. So omega is equal to 2 pi times f. We multiply 2 pi times the frequency here, which will be equal to 2 pi times 2,000 rev per minute times 1 minute over 60 seconds, and that comes up to be equal to 209 radians per second. So this is for part A. For part B, we have to find the linear speed at a point on the edge of the grinding wheel. So this wheel here is rotating, and so at each point here there is going to be some tangential speed v, and we know that the tangential speed v is equal to the radius times omega. So we have to multiply 209 rad per second by the radius, which is the diameter 0.25 divided by 2. And that comes up to be 26.2 meters per second. All right, and in the third part, we have to find the tangential acceleration. So remember, when we have an object, a point moving with some So we actually find the acceleration of a point on the edge of the grinding wheel and its magnitude. So for this rotating wheel, every point here will have both a tangential acceleration, which is equal to the radius times the angular acceleration. And in this particular case, the diameter is rotating at a constant omega. So the acceleration, the angular acceleration is equal to 0. So the tangential acceleration will be r times 0, which will be equal to 0. And then we also have to find, so the tangential acceleration points this way, a tan. But there's also going to be a radial acceleration, which is equal to v squared divided by the radius. So we put in the value of v squared, which is 26.2 meters per second, and divided by the radius, which is 0.25 divided by 2 meters. And that gives us a radial acceleration of 5,480 meters per second squared. Alright, so since there is no tangential acceleration, the only acceleration we have is the radial acceleration, which points towards the center. So in the next problem, you have a child sitting on a rotating merry-go-round, which makes one complete revolution in 4 seconds. So we have our merry-go-round, which makes, so with some radius r. So we're told that it has a period t of 4 seconds. And since it makes one complete revolution, the distance it travels is the circumference, so the linear speed will be equal to 2 pi times the radius divided by the period. And so we are asked to find the linear speed of a child who sits 1 meter from the center. So the distance between where the child sits and the center here is 1 meter. So our r is equal to 1 meter, our period is 4 seconds, so the linear speed will be equal to 2 pi times 1 meter divided by 4 seconds, which is equal to 1.57 meters per second. All right, and then we have to find the magnitude of her acceleration. So again, as she rotates, she may have some acceleration, a tangential acceleration if her omega is changing, and also a radial acceleration which keeps her rotating in a cycle by providing the centripetal force. So since we're not told that there is a change in omega as she rotates, we know that her tangential acceleration is equal to 0, and her radial acceleration will be equal to v squared divided by the radius, which will be equal to 1.57 divided by 1, and this 1.57 squared. So that gives us a radial acceleration of 2.47 meters per second squared. And again, since it's a radial acceleration, it's only going to point towards the center of this circle. All right. All right, for the next problem, problem number 4, we're given an expression for alpha. So alpha is equal to 4.1 t squared minus 4.0 t. And we're asked to assume that the wheel starts from rest. So theta is equal to 0, 1 omega is equal to 0, and t is equal to 0. And we're asked to find omega when t is equal to 7 seconds. All right, so we know that omega or alpha is equal to omega and d omega dt. So if we want to find omega, we have to put the t on the side and integrate both sides. So omega will be equal to the integral of from t0 to t1 of alpha with respect to time. All right, so omega is equal to, so we're going to integrate from 0 to 7 seconds alpha, 4.1 t squared minus 4.0 t with respect to time. And that gives us an expression of, so we integrate this here, so we have 4.1 divided by 3 t cubed minus 4.0 over 2 t squared, which we evaluate from 0 to 7. So we put 7 seconds in here and then subtract that from the expression here with 0 seconds. And so we get omega being equal to 371 radians per second. Right. So in the same way, the displacement will be equal to the integral of omega with respect to time from 0 to 7 seconds. All right, so we have to differentiate this equation again a second time. So this is our expression for omega. We have to take the differential of this, integrate this expression here, sorry, with respect to time to give us a displacement. And so we get 4.1 t to the 4th divided by 3 times 4. So the 4 comes down here and we increase the index, minus 4.0 divided by 2 times 3 t cubed, and we evaluate this from 0 to 7 seconds, and hence we get a displacement of 592 radians. All right, so for problem number 5, we're told that a person exerts a horizontal force. So we have a door and we're looking at it from the top with a hinge. And the person exerts a force 39 newtons on that door handle, which is 84 centimeters wide. So the distance between the pivot point and the point where the force is applied is 0.84 meters. And so we actually determine the magnitude of the torque if the force is exerted perpendicular to the door. So in the first case, this is R, and we are exerting a force an angle of 90 degrees. So for part A, our torque is equal to R times F sine 90. And the radius is 0.84 meters. Our force is 39 newtons. And sine of 90 is 1. So we end up with a torque of 32.8 Newton meters. In the second part, the force is exerted 45 degrees to the face of the door. So this is F1, and F2 makes an angle of 45 degrees. So it's the same expression here, except that the angle here becomes 45. So we end up with the torque being equal to the radius times the force times the sine of 45 degrees. which comes up to be 23.2 newtons meters. So remember, so you see that when you go away from 90 degrees for the force exerted, the net torque gets smaller, which means that the effective force you're exerting to rotate the object is decreasing because of the angle between the force and the radial vector.